Hello dear students. In the last part of our video, we have seen substitution reaction. Today we'll be discussing the second chemical property of haloalkanes, that is elimination reaction. I have taken the example of bromoethane. When bromoethane is treated with alcoholic KOH, we get alkene as the product, along with the byproducts. Now from our 11th class knowledge, we know that this is alpha carbon atom and this is beta carbon atom. Now since hydrogen from beta carbon atom is removed, and therefore this reaction is also known as beta elimination. Halogen is also removed, hydrogen is also removed, and therefore another name of this reaction, dehydrohalogenation. Now in last part of video we have seen that instead of alcoholic KOH, if we use dilute KOH, then we get alcohol as the product. Now when we are using alcoholic KOH, why we get alkene and not alcohol? In presence of alcoholic KOH, why elimination is preferred and not the substitution? The reason lies in the fact that in presence of alcohol, this OH, its lone pair is given to H plus, and therefore in this case OH minus act as a very strong base, and it helps in the removal of proton, and therefore we say that it will cause deprotonation. Now this bond will shift here, and bromine being a leaving group, it will depart, giving the formation of alkene. Now what happens when we are using dilute KOH instead of alcoholic KOH? We will take the same example. Bromoethane, when it is treated with aqueous KOH, now the lone pair of this hydroxyl is given to electron deficient carbon atom, and therefore hydroxyl here will act as a nucleophile, and therefore it gets substituted. Bromine being a leaving group, it departs, and as a result we get alcohol as the product. This is a very important give reason question, that why alcoholic KOH prefers elimination reaction. The reason lying in this fact that in presence of alcohol, hydroxide do not act as a nucleophile, instead it acts as a strong base. Now what if there are more than one beta carbon atom present? From where do the elimination occurs? Let us take one example. So here I have taken the example of 2-bromopentane. In this case we'll have 2 beta carbon atom. Now the question is that from where do the elimination occurs? In presence of alcoholic KOH, we can get pent2-ene as the product, or pent1-ene is the product. Now it is observed that pent2-ene is the preferred product. We get 81% of pent2-ene and we get hardly 19% of pent1-ene. Now why the reaction follows this path? The reason can be explained with the help of a rule called as Saytzeff rule. Now the Saytzeff rule says that double bond will be formed for that carbon atom which has more number of alkyl groups attached to it. The reason is lies in the hyperconjugation. We know that more the number of alkyl groups, more will be the hyperconjugation, more will be the delocalization of electron, and therefore more will be the stability. So what is the Saytzeff rule? We have to remember that the reason why this product is a preferred product, it is because of more than number of alkyl group to doubly bonded carbon atom, more will be the delocalization due to hyperconjugation, and therefore more will be the stability. So now we'll move on to the third part. So this is the third chemical property of haloalkanes, reaction with active metal. Any haloalkane, when it is treated with active metal like magnesium, gives an important class of compound called as Grignard reagent. Grignard reagent is a very important class of compound as it helps to increase the number of carbon atoms, and we can increase number of carbon atom according to the we want. It's not only the ascent of one carbon atom or two carbon atom, but we can increase at a time 3 or more carbon atom also, and therefore Grignard reagent, they are very important class of compounds. Let us take an example of bromoethane. When it is treated with active metal like magnesium, we will get Grignard reagent. Okay. Now what you have to remember about Grignard reagent? Two things. The first one, Grignard reagent reacts basically with carbonyl compounds and cyanides. These are the two class of compounds which show very good reaction with Grignard reagent. How that will be studying later on in our next videos. Just now I am giving you the introduction on this one. And the second is Grignard reagent should be always stored as well as prepared under anhydrous condition. It is because Grignard reagent, as I have told you, they are very sensitive class of compounds and they can react with even trace of water, which act as source of proton, and therefore we get alkane instead of our preferred product. I will give you one example. When any Grignard reagent, if it comes in contact with even a drop of water molecule, then we get alkane, and therefore Grignard reagent has to be always stored or prepared under anhydrous condition. Many times asked, give reason question. So this was about the chemical properties of haloalkanes. Based on all this, now today I will teach you some important conversions. So let us learn some conversions. Conversions is a very important question of your board exams. Two conversions or more than that are sure questions of your board exams. So we'll begin with the first one, prop 1 to 1-fluoropropane. Now in my past videos I have told you that fluorine cannot be introduced directly to any hydrocarbon. That we need halogen exchange method. For halogen exchange method, first of all we have to introduce any halogen in this. So prop 1 I will treat with HBr in presence of peroxide, as I need the substitution at number 1 carbon atom. I will get 1 bromopropane. Then by using the metallic fluoride like silver fluoride, I can get 1 fluoropropane. Let us move on to the second one. Methane to methyl isocyanide. In a board exam, question is asked directly in this way itself, that carry out the following conversion: methane to methyl isocyanide. Isocyanide I can do by carrying out the reaction with silver cyanide, but for introducing silver cyanide I have to introduce any halogen. So first of all, methane, I will try to introduce any halogen. I will carry out halogenation, substitution reaction which proceeds by free radical mechanism. We get chloromethane, followed by the treatment with silver cyanide, we'll get methyl cyanide. Third one, ethanol to ethyl fluoride. Again, fluoride cannot be introduced directly, we need halogen exchange method. So first of all, ethanol we can treat with either phosphorus trichloride or phosphorus pentachloride, or the best is thionyl chloride, Darson process, where we will get chloroethane, and then by using metal fluorides, fluorine can be introduced. So we have got our required product. Next is toluene to benzyl alcohol. This is a very interesting one. Toluene benzyl alcohol means at place of CH3 will get CH2OH. Now we will carry out its halogenation. Now whenever we are carrying out halogenation of a substituted benzene, if carbon atom is directly attached to benzene, then the halogen gets added to this carbon atom, and therefore it is also called as benzylic halogenation. And therefore we'll get the product benzylic chloride. Halogen is got substituted at carbon atom which is directly attached to benzene. Now by using aqueous KOH, this OH will be substituted and we'll get benzylic alcohol. This is one of the important conversions. So let us move on to the next one. The next conversion is methyl bromide to ethanamine. Now we have to increase one carbon atom. If you people remember, I have told you that use of potassium cyanide helps to increase one carbon atom. So first of all, methyl bromide will treat with potassium cyanide. We will get methane cyanide, and then its reduction by strong reducing agent either like lithium aluminum hydride or sodium in presence of alcohol, which was Mandy's reaction. Reduction will occur and we'll get ethanamine. The next conversion is methyl bromide to ethanoic acid. Again we have to increase one carbon atom. So the first step will be same as it is. Methyl bromide treated with potassium cyanide. We'll get methyl cyanide, and now hydrolysis of this cyanide in presence of acidic medium will give us ethanoic acid. Next is 1-bromopropane to 2-bromopropane. Now in this we are supposed to change the position of bromine in propane. So 1-bromopropane. Now I want 2-bromopropane. So first of all I will carry out elimination reaction using alcoholic KOH. Now very easy, HBr. Because in presence of HBr the reaction will follow Markovnikov rule and will get 2-bromopropane as the major product. The next conversion is propene to nitropropane. So for nitropropane, for introducing nitro, we require AgNO2. But for AgNO2 again we need certain halogen. So first of all, propene will be treated with HBr in presence of peroxide. So bromine gets added at first carbon atom. Now we can treat it with silver nitride and we get 1 nitropropane. Now my dear students, before we go on winding up for this chemical properties, I want to tell you about one very important name reaction of this chapter. So I want to throw some light on Wurtz reaction. This you have already studied in your class 11th, and this can be also considered as the reaction of haloalkanes with active metal like sodium. Now any haloalkane, 2 moles of haloalkane when treated with sodium in presence of dry ether, we get alkane with increased number of carbon atom, and therefore this reaction is also considered as ascent of series reaction as the carbon atoms are increased. Let us take one example. 2 moles of bromomethane treated with sodium in presence of dry ether gives ethane. Instead of this chlorine, we will take it halogen. So it will be 2NX. Now the question is why we are using dry ether. The very first thing is dry ether controls the reactivity of sodium. Secondly, the byproduct is insoluble in dry ether, whereas the main product is soluble in dry ether. Therefore, it becomes easier for the separation. Wurtz reaction, again it is an important class of compound. Let us try to do one conversion based on this. The conversion is carry out conversion of N-chlorobutane to octane. So N-chlorobutane, 2 moles of N-chlorobutane, and now I want to just double the number of carbon atom, and therefore I will prefer Wurtz reaction, and we will get octane. Okay. So with this we have completed chemical properties of haloalkanes. Now I would like to give you one word problem based on this chemical properties. So here is one word problem for you people. In word problem questions generally A and you are supposed to identify A, B or X, Y or P, Q, etc. Data is given to you, and based on that you have the questions. Generally these questions are asked for 3 marks. It seems to be very lengthy one, but they are very easy ones. Now as soon as you get word problem, you have to first of all find out various hints given in it. All the word problems will have different hints given in it. Let us solve this. Compound A with molecular formula C4H9Br. So the first hint, the molecular formula of compound is C4H9Br. Is treated with aqueous KOH. The rate of this reaction depends on concentration of A only. So the second hint, rate depends on concentration of A only. When another optically active isomer B, so the next hint is this B is optically active, was treated with aqueous KOH, the rate of reaction was found to be dependent on concentration of compound and KOH both. So for the second case, the rate is dependent on both. Now let us solve all this by using these hints. Compound A, C4H9Br, when it reacts with KOH, that means substitution reaction is there, and the rate depends on only the concentration of compound A. That means it will be SN2 reaction. It will be SN1 reaction, and therefore its molecular formula will be C4H9Br, and this is not an optically active compound according to the information given. Now the second one, when another optically active isomer B, optically active means now this B will have chiral carbon in it. That means it will have 4 different groups attached to a symmetric carbon atom. And this is again proved that when it is treated with aqueous KOH, that means substitution reaction, the rate was found to be dependent on both. Since the rate is dependent on both, that means it will be SN2 reaction. Now chiral carbon, and therefore this will be compound B. This is the isomer of A, as well as it will be optically active as 4 different groups are attached, 1, 2, 3 and one more will be hydrogen, and therefore this will be optically active isomer. So we have got the answer of the first one. Write the structural formula of A and B. The second one, out of these two, which one will be converted to product with inverted configuration? Now we know that specially SN2 gives inverted configuration, and optically active is B, which undergoes SN2 reaction, and therefore the second answer will be also B. It gives the inverted configuration product. So with this we have completed chemical properties of haloalkanes. Next part of the video will be the last part of the video, in which we will be discussing haloarenes. Thanks for watching. Have a nice day.